Hey everyone, lesson 4.3 today on sigma notation. Let's just get going. Okay, so no big fancy introduction, no fractal thing, but we are going to maybe have a little look at some of the examples, but for now we're just going to get right to it. So, sigma notation. What am I talking about when I say sigma notation? So sigma notation is borrowing from the Greek alphabet, and what it is it's a way that we can rewrite series without having to write all the terms out in a long way. This symbol right here, that's the Greek letter, it's the capital sigma letter, so that stands for sum. S is for sigma, S is for sum. So the notation we have right here, this kind of notation, T underscore K, so that's an underscore, that's not a mathematical thing, it's just a way of keeping track. If K equals 1 on the bottom, we have an N up top. What this means is we're going to add up a bunch of terms, and we're going to start with 1 as the very starting number. So what always goes down here, this is the number we start with. This is the number we end with. So in the case where we start with K is equal to 1, TK, T subscript K, is going to be T1 plus T2 plus T3 plus, and this can go all the way up to T subscript M. The letter K is called the index of summation. This can be any letter you want. K is pretty standard, but you can change it to whatever you want. This letter here must match this letter here. That is super important, but you can swap them out for anything you want. If you don't like that, you could go A and then A, but if you make this A, that letter A down there, if you make this A and this is B, well, it's going to be sort of nonsense, so you're not going to want to do that. The bottom number is what we start at, and the top number is what we end at. One thing that always bothered me about this is K equals 1 goes on the bottom, but for some reason we don't write K equals N up top, and that's simply because we just don't need to. It's just unnecessary. Sometimes people are like, well, why can't I just put a 1 on the bottom and some number up top? Well, that's because we need to use some point in this process to define our index of summation. And of course, n can actually be a number. It's not always just going to be n. So it could be 1 to 6. We could start at the number 3 and we could go up to 14. It doesn't really matter. So that's the deal with sigma notation. So some examples of sigma notation are the following. So if we just had sigma with K equals 1 going to 5 of K, then it would be simply you're swapping out K with 1 to get the first term. Then you're swapping out K with 2 to get the second term. It's always plus, 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 because that's what this means. It means sum, and the rest is pretty straightforward. Just a curiosity thing. If you wanted to go 1 times 2 times 3 times 4 times 5, there's other things for this. It's actually a giant capital pi, believe it or not. So this would be like K is equal to 1 to 5, and of K, and that would get you 1 times that. Anyway, this is not part of the course, but that's just in case you're curious. There's other operations, but today and for this course, we're only sticking with adding. Okay, another example would be this third one here, 2 to the power of I. So now I'm using a different letter. I'm defining I equals 3 as the very first number I'm going to substitute I with, and I'm going to go all the way up to 6. You never skip any number, so it's going to go 2 to the power of 3 plus 2 to the power of 4 plus 2 to the power of 5 plus 2 to the power of 6. So we can start at any number we want, we can end at any number we want. We can make it any mathematical operation as well. Here I just had a number. Here I had 2 to the power of a number. Here I've got 1 divided by the number squared. So in this last third example, this is I is equal to 1, and this goes all the way up to infinity, which means we'll just keep going. So we can say 1 over I squared. Well, the first one would be 1 over 1 squared, which is 1. The next one would be 1 over 2 squared, which is 1 over 4, 1 over 3 squared, and it just keeps going. And if it keeps going, you put the dot, dot, dot there. It's not really a hard and fast rule for how many of these terms you have to list out, but I would list at least 3 or 4 of them. Okay, before we get using this stuff, just a couple handy properties. You might even say some useful properties. LOL. But we're going to just remember these as we're moving forward. And if they make sense, that's great. If they don't make perfect sense, well, we'll try and make some sense of them. So the first one here says, if you've got a couple things added together and you're doing a sum with both of those things, I guess it's kind of like a sum of a sum, you can actually split it up into two different sums. So this would be like if we had, let's see, k, so let's see, k is equal to 1, goes up to 4, and this would be k plus, and I'll just pick a number here, this could be 2. Okay, so what we could do is we could do, whoops, let's not write that. We could say the first one will replace k with 1, so it would be like 1 plus 2. That would be the first term. And then I'd go from k is equal to 1 to k is equal to 2. And I'd go, okay, well then that's 2 plus 2. And then the next term would be 3 plus 2. And then the next term would be 4 plus 2. And we'd be done because we finally hit our limit at 4. So we could do it that way if we wanted, but maybe a simpler way is we could actually do this. We could say this is the same as the sum of k is equal to 1, here's k, here's 4, and then I'll actually add it here as well. And here's the number 2. So what we can do is the first one is going to look like 1 plus 2 plus 3 plus 4, and then this guy is actually going to look like, well, see, we don't have a k in here, so it's basically saying let's just take this number and we're just going to add it 4 times. So when you don't have a k or any index of summation here, you just add it up as many times as it says to. So if we start at 1, the first term would be 2, the next term would be 2, the next term would be 2, and the next term would be 2. So you could add it up this way, add these up separately, so this would be 10, this would be 8, and you could add them up and get 18. So you could do it that way if you liked. The second property, which is even more useful and simpler to do, is this one here. Now I didn't include any limits here in the first one, right? You'll notice that's just sort of a blank generic sigma. This one I did because I wanted to make clear c is the constant and a to the power of k. It doesn't have to be this operation, but this guy actually depends on k, so it's not a constant. Any constants you can always factor out, so the c can come out. So again, this would be a situation where we have like 2 times, it could even be 2k or 2 times 3 to the power of k. It doesn't really matter. And if this was k is equal to 1 to 4, one way we could do this is we could say 2 times 3 to the power of 1 plus 2 times 3 to the power of 2 plus 2 times 3 to the power of 3 plus 2 times 3 to the power of 4. But you can see that 2 could have actually just factored out of the whole thing, and we'd have 3 to the 1 plus 3 to the 2 plus 3 to the 3 plus 3 to the 4. So what we would normally do is we would normally actually just take this 2 and we would factor it out in front right off the bat, and we wouldn't have to worry about it. Okay, so 2 properties, we might use those from time to time. Okay, so here's the first example, pretty simple. My beautiful face is covering this up. There we go. For each series, determine how many terms there are and then write each series in expanded form. So here we can see that we've got k is equal to 1, we're going up to 4. Now a little formula for you here is the number of terms. You can kind of logic this out. If you start at 1 and you go to 4, you've got 4 terms. But if you really want a formula for this, you take the top number, you subtract the bottom number, and that would be 4 minus 1, which would give you 3, but we know we have 4 terms. We know we actually have to include the 1, the 2, the 3, 4. So we'd actually just add 1 to it. So we could use this formula here. This is sort of like a formula, I guess. You go 4 minus 1 plus 1. We'd have 4 terms. Sometimes when the numbers get a little bigger, you might want to actually use that. All right, so writing this out in expanded form, this would be 3 to the power of 1 plus 3 to the power of 2 plus 3 to the power of 3 plus 3 to the power of 4. So there's 2 ways we could do this. We could say, well, we've got a geometric, this is a geometric, by the way, this is a geometric series, and we could think of it as 3 plus 9 plus 27 plus 81, or we could say we've got r is 3 and we're going up, and we could use a formula. But you know what, when it's simple like this, I wouldn't even bother. I wouldn't use the formula, just calculate it all out. So let's see if I can do this in my head. So 3 and 27 makes 30, 9 and 81 makes 90, 30 plus 90 is 120. Ta-da. Alternatively, or you could say the sum of 4 terms is equal to t1 1 minus r to the power of 4 over 1 minus r. And this would totally be overkill, but you could do it. So we can see that r, we're multiplying r is equal to 3, because every time we're going up, we're multiplying by 3 every time. So this would be 1 minus 3 to the power of 4, and this would be 1 minus 3. And this would super overkill it, but 3 to the power of 4 would be 81, so minus 81. This would be over negative 2. So let's see, what would this be? This would be 3 times negative 80. 3 times negative 80 over negative 2. Now we'd cancel those out. It would be 3 times 40. And we'd wind up with 120, which is precisely what our answer was. But we just did it manually because it was still pretty short. Okay, next one. So x is equal to 3, and we have an x. The letters match, so that's fine. There's no problem there. And we're going from 3 to 11. So how many terms do we have in total? The number of terms, I'll just write it down here. The number of terms equals 11 minus 3 plus 1. So if we actually wrote this whole thing out, we should have 9 terms in total that we're writing. And instead of writing out the 4 in every case, I'm actually going to factor that bad boy out, and I'm going to write it like this. So here's 4 sigma, and then this is 1 over 3 to the power of x. So if I wrote this whole thing out, this would be 4, and then big brackets for the rest of the sum. 1 over 3 cubed plus 1 over 4 cubed plus, sorry, brain stopped. The 1 over 3 never changes. This becomes to the power of 4, and this would be 1 over 3 to the power of 5, and we would keep on going dot, dot, dot. We would go all the way to 1 over 3 to the power of 11. It's not really necessary to write every single term out. That would get pretty monotonous. Okay. Now, in this case, you could sit there and crank it out manually, but I'm definitely not going to do it. So what I'm going to do to calculate the sum, I'm going to say S, and here's the part where you have to think about this a little bit. We're not going to say S3, we're not going to say S11. It's 9 terms, so we're going to write S9, because we're summing up 9 terms, the first 9 terms here. So what is the first term? It's T1, 1 minus R to the power of 9 over 1 minus R. So what we have to do, and I'm just going to change my color here, we would actually have to look at this and go, well, if you look at this structure here, we can see 1 over 3 to the power of x. That's the multiplying factor. So whatever the base of the exponent is in general, that's what r is. And I'm only going to give you geometric series here, so we can always kind of use that idea. The 4 is just going to hang out. Now we do, of course, have to figure out what T1 is. If we look at this, if we did multiply the 4 back in, because we actually would have to do it to use this formula, although there's some arguments that you could actually factor the 4 out, stick it out here, but I don't know if I want to get that complicated right now. Oops. So what we'd have to do is we'd have to figure out what T1 is. If we multiplied that in, we would have 4 times 1 over 3 to the power of 3. So I'm actually going to write that as 4 over 3 cubed, which is 27. So for me, it actually is easiest if I just multiply the 4 and just have it. So what we're going to do here is now we're going to go, this will be 4 over 27. This will be 1 minus 1 over 3 to the power of 9. And then this will be divided by 1 minus 1 over 3. At this point, you probably want to pick up a calculator. Now, I'm going to go ahead, and I'm not going to use that stupid Windows calculator this time. I wasn't very happy with it. I'm actually going to go, and I'm going to, oh, there's the Serpentines carpet. I'm actually going to go, and let's share that. My apologies. I didn't mean to do that. Okay, I'm just going to go here. Yeah, it's ready to go Carnival Executives. Okay, so we're going to go Desmos calculator, and then we're going to use that instead of the horrible Windows one. So we would have to go calculate this using the Desmos calculator. So this is not really super exciting part, but we'll just do it. We'll say 4 divided by 27. We're going to multiply that by 1 minus, now I'm going to write 1 over 3 here, close it up, and I'm going to raise it to the power of 9. And then I'm going to close that all up, and I'm going to divide this by 1 minus 1 over 3. Okay, so this says 0.22222. All right. Okay, I just had a little moment there. I realized what I was doing is I was looking at this and saying 4 times a third couldn't possibly make sense. And then I realized 4 times 1 over 3 to the power of 3. So that's like 4 over 27. All right, so now I'm actually pretty satisfied. This answer surprised me at first, but now it makes some sense. So it's like 0.22222. Okay. So I was just doing the common sense thing where I was trying to look at this and say, well, if T1 is 4 over 27, then adding more stuff to it should work to get it to something slightly bigger than whatever 4 over 27 is. And I'm confident 0.2222 makes sense. Okay, here's part C. So what I'm going to do here is I'm going to look at this one, and we've got a similar situation. We've got -2 to the power of k. So that's something that looks like a geometric series. And now I'm just going to think about how I would deal with this. I don't like when I have something plus something. So for me, I'm kind of a big fan of adding 2 different sums together. But first, let's just take a look here, and let's look at the number of terms. So the number of terms would be 5 minus 3 plus 1. I mean, we can probably even just guess there's only 3 terms here. There it goes. I've got 3 terms. If I wrote this out, this would become, now I'm going to use that property that I was talking about before. So let's actually do this. Here's this. Here's this. And then I'm going to split it up. Now this one's kind of funny. K is equal to 3 to 5. There is no K over here. But we can simply work that out using a little bit of common sense. Okay, so this one would be -2 to the power of 3 plus -2 to the power of 4 plus -2 to the power of 5. That's what this first guy would be. That big brackets. This one here, I just want to make sure we're not overthinking this too much. This guy right here, there's 3 terms, and each term is equal to 1. So this is simply going to become 1 plus 1 plus 1. It's that simple. If you want sort of a formula here, or like a rule, I guess, if this was A and this was B and this was just, we're going to call this C for like a constant, this would be C, and then you'd have to multiply it by how many terms you have. And the number of terms you have would be B minus A plus 1. So this is your number of terms, and this is the value. So in this case, it would be 1. So we have, it goes from 3 to 5, 1, we have k is equal to 1. So this would become 1 multiplied by 5 minus 3 plus 1. Anyway, that's equal to 3. I feel like that's almost overcomplicating something relatively simple, but if you're really into like a general formula for this whole kind of thing, you can use that. Okay, and then it's just a matter of actually working this out. We don't really have to use a formula for this, so I'm just going to work out -2 to the power of 3 is -8. This will be +16. This will be -32, and then the rest, this whole thing will be equal to 3. So we work that out, and let's see. So -40, -37, -27, I think -21. I hope that's right. I guess I should have boxed my other answer up there. Okay. This one here, we'll just rip through the last of these pretty quick. This one, we've got k is equal to 2, and we've got infinity. So how many terms do we have? It would be incorrect if we said infinity minus 2 plus 1. It's just infinity. There's no adding or subtracting to infinity. So we'd start by writing this out. We'd write 2 times 0.1 to the power of 2. And then this would be plus 2 times 0.1 to the power of 3. Going on forever. So we have an infinite sum. So what we can see here is this is T1. T1 is equal to 2 times 0.1 squared. Now I'd actually really prefer to write this as 2 times, oops, 2 times actually be my favorite way of doing that. And we can see that as we're going here, we can see that r is equal to 0.1, but I'd actually rather write 1 over 10. So putting this all together, s infinity, this, which would be 2 over 100, 1 minus 1 over 10. So that would be like 2 over 100 over 9 over 10, which is like 2 over 100 multiplied by 10 over 9. So this would work out to be one of those and one of those would cancel, and we'd have 2 over 90 would actually be the best sum. Okay, last one here, pretty similar to the other ones. If you have not sat and tried to actually do one of these yourself, definitely pause it and try this yourself. So my first step would be to go 3 and then like factor that 3 out, and then we'd have infinite k is equal to 1. I've been saying the number of terms the whole time, so let's just write it down. Number of terms equals infinite, and then we'd have 1 over 2 to the power of k. So this would be 3, and then it would be 1 over 2 to the 1 plus 1 over 2 squared, dot, dot, dot. Okay. So in this case, I'm actually going to treat this as my sum. Here's my sum of infinite terms. I'm actually going to leave the 3 out. So I didn't do this before in the previous example where I sort of mentioned I could, but in this case, I'm actually going to say this is 3 times infinite sum. So I'm actually just going to take that 3 and leave it on the outside, and you're totally allowed to do that. So there's 3, and we're multiplying it by t1 over 1 minus r. So what we do is we just have to make sure we're careful with what t1 is. In this case, this is t1. It's a half. And we can say also that r is equal to a half, because that's what's constantly being multiplied. So this value here, that's r. So this would be the infinite sum. And I really like infinite sums because they actually have much nicer math, so we can usually work this out in our heads. And well, this is interesting. So 1 minus a half is a half. So a half over half is 1, so it's got to be 3. That's an interesting result. Let's just take a second. Does that make sense? If you take a half and you add to it a half squared, that's a quarter. Okay, think about this. What's a half plus a quarter plus an eighth plus a 16th plus dot, 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 dot. That's actually going to wind up equaling 1. There's a fun little factoid for you. If you want to travel some distance, in fact, if you're a curious person, I believe the correct spelling of the name is Zeno. If you've ever heard of Zeno's paradox, it's this idea that you can never get anywhere, because if I was to say travel from point A to point B, I'd first start by traveling half the distance, and then I'd travel half of the remaining half, which would be a quarter, and then I'd travel half of that remaining half. And I can never actually, I'm going to keep adding half of a half of a half, and in theory, it should never equal to 1, although a mathematician would argue that it actually does. Anyway, if you're a curious person, go look up Zeno's paradox. It's quite a neat little thing. Okay, so example 2. Write each of the following sums in sigma notation with k equals 1 as the first term. So the way we're going to look at this is we're going to say, okay, well, I've got a sum, so I'm going to write sum. We're told k is equal to 1. How many terms do we have in the sequence? It goes dot, 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 so we're going to go up to infinity. And then we have to have a way of representing this. So what we can see is this is geometric. R is equal to 2. And the first term, t1, is equal to 2 as well. So there's a couple ways we can think about this, but the easiest one is to probably say that the very first term has a value of 2, and we can see that the next term has a value of 2 squared. In fact, you might even find it useful to just rewrite it as 2 to the 1 plus 2 to the power of 2 plus 2 to the power of 3, and so on. So we can actually see that the easiest way of doing this would just be to say 2 to the power of k. And that would be it. So k is equal to 1 to infinity, and everything's going to be powers of 2. There's not really a formula way of doing this so much as a look at it and use a little bit of common sense way. Okay, the next one. So we have a finite number of terms. We have 5 terms in total. So this tells us that we're going to have to start our sigma from k equals 1. We're going to have to go up to 5. Now I start with 9. And then every time I go forward, I can multiply by negative a third. I can see that the signs are alternating, so r is equal to negative a third. So there's a couple ways you can look at doing this. You can say that maybe let's start with 9 as the very first term in this case, and we're multiplying everything by 1 over 3. Now, if you do it that way, well, let's make that negative. If you do it this way, you got to keep in mind k is going to start at 1. So if we just simply put k there, it's going to be 9 times negative 1 over 3 for the very first term, and that's not the case. We actually want this exponent to have a value of 0 for my first term, because 9 times anything to the power of 0 is going to give us the 9 that belongs up there. So the modification we're going to make is we're going to make this k minus 1. And that's probably the easiest way of doing it. One thing just worth thinking about, totally optional, is you might realize these are all powers of negative 3. So a totally optional way of doing this, or you could have said k is equal to 1 to 5. You could have said negative 3 to the power of, well, the first term would have been negative 3 to the power of 2, and then the next one's negative 3 to the power of 1, and then the next one's negative 3. So you could have actually thought of this like, this is like negative 3 to the power of 2 plus negative 3 to the power of 1 plus negative 3 to the power of 0, and so on, actually. So another way you could have done this is you probably could have done this, and I'm actually sort of thinking here, I need the values of the exponent to actually decrease. So we probably could have said 3 minus k. So when k is 1, 3 minus 1 would have been 2, and then it actually increases from there. This would have been a possibility as well. Total preference here. I think some people might be favored toward the second one because it's a little more elegant. Anyway, there you go. One thing I just should mention as well, don't you dare try and multiply the 9 in here and write like 9 over 3. That's definitely not going to work. The r value itself is what goes as the base of the exponent. Okay, and then the last one here, or the last of the ones that don't have a picture, what we have is we got a bunch of terms. We have a finite sequence. Now, I don't actually know how many terms there are, so this is where we're going to have to just think a little bit. This can be rewritten as 3, and then r is equal to 2. So this is 3 to the power of 2 to the something, to maybe the k. That's kind of like a general idea. The first term here, actually, I'm just going to erase that here. The first term I can see is 3 times 2 to the power of 0, and the next one is 3 times 2 to the power of 1, and then we've got 3 times 2 to the power of 2. Okay, now this one here, this is sort of interesting. So what I'm going to do is I'm going to jump out here because I got to work this out. We're actually going to learn a way of doing this properly, but it's not really this unit yet. I'm going to go 3072. And first of all, I'd like to figure out what power of 2 there is. I'm going to divide it by 3. So I'm going to say 3072 equals 3 times 2 to the power of x. So the first thing I'm going to do is divide both sides by 3. So when I divide it by 3, I get 1024. So this is like saying 1024 is equal to 2 to the power of x. So there's a systematic way of doing this using logarithms, but that's actually in the next chapter. Right now, you're probably fine just guessing and checking. So what I'm going to do is I'm going to erase this, and I'm going to say 2 to the power of, and I'm just going to take a guess. I'm going to say 2 to the power of 10. 2 to the power of 10, look at that. It's 1024. So if you get it wrong, you just keep trying. But we can see that x is equal to 10. So if the first term, t1, is there, and there's an exponent of 0, then what term would have an exponent of 10? We should be able to deduce this would be t11, because t1 has an exponent of 0, so the exponent is 1 less than the term. Okay, so this tells me, therefore, there's 11 terms. And I've done most of the heavy lifting, actually, because now the sum can be represented as, and I'll use k is equal to 1 to 11, and then we can see we've got 3 multiplied by 2 to the k minus 1, because the exponent there on the first term should start at 0, and if k is at 1, well, we need to do something to just knock it down. Okay, there we go. total length of all the lines in this finite section of the Cantor set, we can see that the length of the lines would start with, and we're just going to assume this is equal to 1, as we've done before. So it's equal to 1 plus, now each one of these is equal to a third, but we've got 2 of them, so we're going to do 2 times a third here. Each one of these are all thirds, right? A third of a third of a third. We've got 4 times a third of a third, which is 1 over 9. Here we've got 8 different ones, 1, 2, 3, 4, 5, 6, 7, 8, and then we've got 1 over 27, and so on. So this is going to be like 1 plus 2 times a third, whoops, plus 4 over 9, and so on. So if you're looking at this, this is a finite section, so we're just going to think, how many do we have? We've got 1, 2, 3, 4, 5, 6, 7 rows. There are 7 rows here. So the length we could express as the sum from k is equal to 1 to 7, because we're going to have 7 terms. And how do we represent this? We can see that r is equal to 2/3. So we're going to definitely have a 2/3 to the power of something. And are we having anything we need to multiply it all by? I don't actually think so. I think if we do 2/3 to the k minus 1, we're all set. So when k is equal to 1 for the first term, the exponent will be 0. We'll have a 1. And that should be okay. I got one more question here. Now, this is not a super crucial thing, but I think it's just a really curious one, because rational numbers or irrational numbers have a tough time being expressed as a number, but we can figure out ways of expressing them as infinite sums. So there's actually a ton of different ways this is possible for important numbers like pi or whatever, but this is one of the more curious ones, I think. This is one of the simpler ones. So if you actually want to know the value of pi, you can go pi squared over 6 equals 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared, and so on. So just for fun, pi squared over 6 rather, can be expressed as, we can see this is a sum, an infinite sum, so we'll start with k is equal to 1 to infinity. And we could actually work this out as 1 over 1 squared. So the numbers here, they're just going up by 1. So there's our k, and it's always squared. And that's basically it. If we really wanted to isolate pi, we could move the 6 over and say pi squared equals 6 times that sum. And we could write it like this if we wanted as well. And if you're really were keen on isolating pi, you could square root both sides, and you could do something weird like this, which is, it's possible, but it's just sort of ugly and weird. Anyway, this would be a way of actually calculating pi. Now, if you've never seen this before, it's kind of interesting to work out. We can jump over to something like Desmos, and we can just try this. So what we'd have to do is work out the first 5 terms. So we'd put a 6 in there, and then we'd start brackets, and we'd go 1 over 1 squared, but I'm not going to bother writing that, so I'll just write 1. 1 divided by 2 squared, it's easier for me to just write 2 times 2, plus 1 divided by 3 squared, plus 1 divided by 4 squared, plus 1 divided by 5 squared. Okay, so I said just use the first 5 terms to approximate it here. We get 2.96. Yeah, it's not so bad, but it could be better. If we keep on going here, and I'll leave this as something you can try, but if you want to keep on going, you keep adding terms like 1 over 6 times 6, and you keep on going. If you kept on going long enough, you'll get to 3.14, but it's going to take you a while. I tried it before. I don't want to deal with doing that all again. So anyway, this would be like the root 6 over 1 squared, 1 over 2 squared, 1 over 3 squared, 1 over 4 squared, 1 over 5 squared. Most of the point of this, whoops, that was not supposed to be 5. Most of the point of this is just to show how you can write something here. Here's a pop quiz question. Is this a geometric series or not? The answer is absolutely not. So this is 2.963. 2.963. Not the best approximation, but it's something. Here's one more number, and this one's worth really mentioning because this is going to be very important as we move forward. It's called Euler's number. It's E. Most people haven't heard about this, but it's equally as important as pi, if not more important, especially to calculus. There's one other thing I want to teach you here. When you see an exclamation mark, it's actually pronounced as factorial. So the way a factorial works, if you had 4 factorial, it's 4 times 3 times 2 times 1. 10 factorial would be 10 times 9 times 8 times 7 times 6, all the way down the line. There's a definition here that 0 factorial is equal to 1. 1 factorial is also equal to 1. So just some things. So this is a really nifty number. If you don't know what the number E is, go to Desmos, erase all this business, and just type the letter E. E. There it is. 2.718, blah, 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 blah. It's an irrational number. It has a lot of 8s and 2s and stuff, but I promise you it doesn't repeat. So E is very important. We'll talk about its significance later, but just to see, we can actually work this one out as well. So let's first of all turn this into a sum. So this is the sum of, take a second, try this yourself if you haven't thought about it. It's actually a pretty easy one though. We could say that K is equal to, now this time I'm going to write K is equal to 0. Because it's easiest if I say 1 over K factorial. And that's it. Because it's going to be 1 over 0 factorial plus 1 over 1 factorial and so on. So if we're actually very curious here, we can work this one out. We can say, here's the first 5 terms, 1 over 2. Sometimes it's fun to yell when you're doing factorials like it is an actual exclamation mark, like 1 over 4. Okay, so what is this actually equal to? Let's just try it on Desmos just to see here out of curiosity. This will get us 1 divided by 0 factorial, which it actually understands as 1, plus 1 divided by 1 factorial, 1 divided by 2 factorial, plus 1 divided by 3 factorial, and then finally plus 1 divided by 4 factorial. And we're actually pretty close. That's 2.708, whereas it's actually 2.718. And if you keep on going, and I'll let you try it, you'll actually get remarkably close. So that's 2.70833. So that's about 2.708 dot, 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 dot. Cool. Okay, so that's it. More on E later. It's going to be very important later on, but for now I just wanted to give you a little bit of an introduction to it. All right, thanks for watching. Goodbye.